Hello everyone, Changpeng and I are coming from Intel storage software team. We are talking about the evolution of SPDK towards secure container storage service. SPDK is a storage performance development kit. It provides a set of tools and libraries for writing high-performance, scalable, user mode storage applications. SPDK vhost is one SPDK-provided application. As a high-performance storage virtualization solution with flexibility and robustness, it's already widely deployed by lots of CSP and enterprises in their infrastructure. In this topic, we start at the consideration on VM-based secure container. From recent papers and reports of AWS or AliCloud, secure container is the bedrock for their public cloud container service. So it is popular in CSP. And commonly, secure container is virtual machine based, like Kata containers. Here, the evaluation work we have done is based on Kata containers. Since it is virtual machine based, can SPDK vhost directly be applied to Kata containers? Let's take a look at the characteristic of secure container. The first characteristic is high container density. Not like a traditional virtualization scenario that only tens of VM are running in a server. Secure container serve more than 1,000 of containers on one single host, which means more than 1,000 of lightweight virtual machines are running on a single host. The second item is resource over-provisioning. CPU and memory resource will not be planned and pre-assigned to specific virtual machines. Probably, these resources will be scheduled to different container dynamically, and they are always taken seriously since there are a lot of containers. And commonly, containers do not only focus on extremely high performance, but it also focuses on flexibility and robustness. The first problem we might with SPDK and secure container is about the high container density. SPDK application uses polling mode, which is an endless while loop to poll each device, check and process their requests. For vhost device, SPDK polls each word queue in rounds. Polling mode with this type of application framework is good and efficient for heavy workloads. But for container, their IO workloads are not always so heavy. So when containers are in high density, polling to query massive word queues is not efficient at all. The second problem is about CPU and memory resource over-provisioning. When some CPU cores are running SPDK vhost, then this cores will be occupied or pinned by SPDK vhost all the time due to polling mode. Just like our slogan, "Don't interrupt me, I'm polling." For memory, due to user space device DMA operation, SPDK requires memory to be pre-allocated as a huge page memory. The memory pre-allocation and the CPU occupation required by SPDK vhost are barriers to over-provision all server resources to container.
Okay, towards the secure container, can we involve SPDK applications to be interruptible? Let's first look back on SPDK internal. One of the primary aims of SPDK is to scale linearly with the addition of hardware. To achieve this, SPDK execution unit must be independent from one another as much as possible, and avoid soft locks. Instead of placing shared data in a global location that all threads access after acquiring a lock, SPDK takes a different approach altogether. SPDK will often assign that data to a single thread. When other threads want to access the data, they must pass a message to the owning thread to perform the operation on behalf of the threads. This strategy, of course, is not new. For instance, it is one of the core design principles of Ericsson-Long and is the main concurrency mechanism in Go language. SPDK provides several layers to construct message passing infrastructure. The most fundamental libraries in SPDK, for instance, don't do any message passing on their own. They depend on SPDK's thread abstraction. SPDK thread abstraction provides a basic message passing framework and defines a key primitives. First, SPDK is an abstraction for a lightweight stateless thread of execution. A low-level framework can execute an SPDK thread for a single timeless by calling SPDK thread pool function. The lightweight thread is the fundamental abstraction for threading in SPDK. There are also a few additional abstraction layers on top of the SPDK thread. One is the SP polar, which is an abstraction for a function that should be repeatedly called on the given thread. And the other one is the SPDK message, which is a function pointer and a context pointer that can be sent from a thread to another. The library also defines two additional abstractions. One is SPDK device, and the other is SPDK channel. In order to implement a message passing strategy, the code would describe some object within global state and also some cross-thread context associated with that object. This makes SPDK very portable to a wide variety of asynchronous event-based framework. SPDK provides a framework for writing asynchronous pull mode, shared nothing server applications. The framework defines several concepts: reactors, events, and lightweight thread. Reactor, the event framework spawns one system thread per call. Reactor stands for the system thread. Events, reactor connect each other with lockless queues. Events can be passed between the reactors. The lightweight thread is the representative for SPD thread, who is a stateless execution unit. A lightweight thread in SPD is linked in a list inside a reactor. In this event framework, a reactor running a while loop round and round pulls its event queue process incoming events, also pulls the SB thread attached in it, so that the polar are executed. This framework shows how to put SPDK components together. SPDK community uses it to build their applications like vhost target. It glues SPDK components in a pooling programming model. So here for SPV host target is applying related components in SPDK with userspace and pooling techniques. When run one SPDK host target, First, the first step is when create a vhost device, SPDK will create a specific SPDK thread. Inside the lightweight SPDK thread, pullers are registered to take and process our request in virtual queues as the front-end, block device as the backend. All functions are driven by pulling execution in reactors.
Now we want to evolve SPDK application in interrupt mode. It should be compatible with current SPDK event framework and SPDK thread abstraction, which is created for effective message passing, asynchronization, and run-to-completion characteristics used by applications inside SPDK. The interrupter abstraction objects now are based on EPO and EventFD on Linux platform. It is the core concept to achieve interrupt wait notify mechanism. Initially, it is one EPO instance with registered target file descriptors. Different target file descriptors represents different interrupts or event source. For example, EventFD is used for internal queue notification. SocketFD is used for network data coming or out notification. TimerFD is used for periodic work. VFL EventFD can be used for user space device interrupt. The most important one is cascading the EPO instance for grouped events. If we map the interrupt abstraction of EPO group, then we can get SPDK reactor and SPDK thread to be interruptible. When apply interrupt abstraction to reactor, the reactor itself contains one top-level EPO instance and one event FD represents for its internal event queue is registered to the EPO instance. What's more, other registered file descriptors are all sub-level EPO instance, which represents SPDK threads who is attached to this reactor. As we just said, SPDK thread itself also contains one EPO instance as a central role. Then we can register corresponding file descriptors to the thread EPO instance instead of registering polars to SPDK thread. For example, at first, message queue polar or message queue process event can be replaced by one event FD for message queue. Polars with interval time can be replaced by timer FD. Hardware queue polars for NVMe device or whatever device can be replaced by VFL event FD. NBD polars can be replaced by just registering its PEP FD to the EPO instance. ALO BDEV can use event FD together with libALO. If SOC group apply the interrupt abstraction for its connections, then SCSI or NVMf polars can be triggered directly by the SOC group interrupt. After applying interrupt abstraction into reactor and SPDK thread, then one SPDK application can run in such a methods to get itself running in interrupt mode. The application will do block wait on reactor EPO instance and do non-block wait on SPDK thread EPO instance. Then the system threads of the reactors will only get blocked at the reactor EPO instance. If the EPO instance of reactor wakes up from its event queue, then it directly comes to the event queue and process the event. If it is waking up from one SPDK thread message, then the reactor will come to the specific SPDK thread, and then the thread will process the message queue. If there is one libalo completion, then the reactor epoch instance will wake up and come to that specific SPDK thread, and then the thread will come to process the libalo event. Each time the process is completed after waking up, the system thread will come back to reactor and block on reactor epoch instance. SPDK further provides a full block stack as a user space library that performs many of the same operations as a block stack in an operating system kernel. All of them are designed around message passing instead of locking, and most of the SPDK libraries makes several assumptions like message passing, event, co-routing, or lightweight threading framework. So if the underlying threading model is interruptible, then many of the libraries inside the SPDK can run directly in interrupt mode. For example, the basic BDAL modules like read BDAL, speak BDAL, GPT, or malloc BDAL. For SPDK, blob store and its upper layer logic volume, they can all run directly in interrupt mode without any modification. For SPDK blob FIs and its fuse module, they can also run directly in interrupt mode without any modification. So here we have prepared a minimal set of interruptible vhost target in interrupt mode for secure container evaluation based on some interrupt mode patches. It will use Linux ALO BDAL as the storage backend. It will export Linux NBD service to host, and it will provide vhost block device to the lightweight virtual machine of secure container. A flexible block stack with logical volume are there for advanced block operations. Users can also manage this evaluation application still by SPDK RPC methods. The difference of this application with general SPDK application is that it won't be polling or occupying CPU cores anymore. When there is no workload, its CPU percentage is lower than 1%. A set of tools are provided by SPDK. Some of them are also easy to run in interrupt mode. For example, the BDAL perf tool. It is a benchmark tool of SPDK block device for thread and event work cost. A set of tools are provided by SPDK. Some of them are also easy to run in interrupt mode. For example, for BDAL perf tool, it is a benchmark. It is a performance A set of tools are provided by SPDK. Some of them are also easy to run in interrupt mode. For example, for BDAL perf tool, it is a performance benchmark tool of SPDK block devices for thread and event framework cost. We have added a parameter to BDAL perf to set interrupt mode flag. With this simple modification, we got some brief performance evaluation on interrupt mode for you to have a preview. Of course, there is an obvious performance drawdown when run BDAL perf on memory BDAL. It shows about the throughput of interrupt mode is less than 1/3 of the throughput of the polling mode. When run BDAL perf on NVMe-based ALO BDAL, it shows about the throughput of interrupt mode is around 5 to 8% worse than polling mode. This is not good for extremely high performance situation, but for the container scenario, it would be enough.
Okay, the last part, on top of interruptible SPD application, we can provide a secure container storage service. At start, the most straightforward step is to providing device volume from SPDK vhost by Docker command. Provide a volume service to Kata containers via the interruptible SPDK vhost target. And SP logic volume can do same provisioning and snapshot like logical volume and device mapper. SP logic volume provides basic functionalities to meet a container rootfs. Provide rootfs service to Kata containers via the interruptible SPDK host target and the container D. How users run SPDK is much more diverse than we expect. From SP GitHub issue and Slack channel, we realized that there are users who run SPD inside the Docker container. When containering an SP application, there are no SPDK specific changes needed. However, general SP application always requires dedicated CPU cores and huge memories. So exclusive resource occupation is a main issue for containering an SPDK application. If SPD application inside the container is running in the interrupt mode, also with non-huge memory, the container density will not be impacted by SPDK container. Currently, only basic interrupt mode is supported. If we want to get SPD to be more suitable to secure container scenarios, from container infrastructure to container instance. So let's give a summary first. Pulling pinned CPU and huge memory pre-allocation can be avoided from non-performance situation. With the interrupt mode, SPD host will be a good choice to provide a storage service to secure containers. For the future evolution, we may add interrupt support on userspace hardware block device backend, such as the NVMe driver and the block layer, without device driver and the block device layer. And also, we can add interrupt support on modules related with the network protocols, such as NVMe or Fabrics and the iSCSI. Also, we in running mode switch between the pulling and the interrupt. The last is we can official non-huge memory support for all the non-DMA SP application. That's all for today's presentation. Thank you.